It's one thing when artificial intelligence writes a slightly surreal poem for you, or like generates an image of a cat riding a bicycle.
Right, yeah.
Like if the generative model hallucinates an extra finger on the cat's paw, you just laugh and scroll past it.
Exactly. It's just a funny glitch.
Yeah, but when we start handing over the keys of autonomous drug discovery to AI, when an algorithm is literally tasked with designing a life-saving therapeutic from scratch, well, a hallucination is no longer a funny digital glitch.
Oh no, it's a fundamental failure.
Right. I mean, if a model invents a molecule that literally breaks the laws of thermodynamics or proposes a chemical bond that cannot physically exist, it could cost a research pipeline years of wasted time.
Yeah.
And billions of dollars.
Well, billions, yeah, absolutely.
So the question we are exploring in our deep dive today is, how do we stop the AI before it ever leaves the server? Today, our mission is diving into a stack of highly technical reports analyzing a new paradigm called scientific intelligence.
Which is just a massive shift in the field.
It really is. We're looking at the strict physical validation frameworks that keep these massive multi-agent AI suites, actually grounded in reality. Okay, let's unpack this.
Yeah, so it's a profound shift in how we approach computational biology. I mean, we are moving away from traditional high-throughput screening, which, relies heavily on human intuition and just massive physical trial and error.
Right, throwing everything at the wall to see what sticks.
Exactly, and moving toward a system where AI suites handle the entire pipeline. They identify the biological target, and then they design the exact molecule to bind to it. But you hit the nail on the head regarding the major hurdle here.
The hallucinations.
Right. The digital vision of a protein and the subsequent design for a drug, they must map perfectly onto the physical universe. If the AI's internal representation of a target doesn't match the actual biological reality,
then any drug it designs is essentially a phantom key for a phantom lock.
That's perfectly put, yeah.
Yeah.
It's useless in the real world.
Right, which means we need a reality check. And looking through these sources today, that reality check is anchored really heavily in cryo-EM, cryogenic electron microscopy.
Yes.
But what I want to understand is the translation layer. Like, it's one thing to have a high-resolution cryo-EM scan of a protein, right? We have the physical evidence.
Sure.
It's entirely another to get a predictive AI engine to automatically benchmark its own digital assumptions against that physical scan. Like, how does it compare its architectural blueprint to a photograph of the real building?
Well, that translation layer is where things get highly sophisticated. It's done specifically through a process called high-resolution benchmarking.
Okay.
So modern structure prediction engines, like one highlighted in the reports called IsoDDE, they don't just generate a blind guess.
Right.
They actively benchmark their accuracy against high-resolution cryo-EM structures, usually in the 2 to 4 angstrom range.
Wow, so really high resolution.
Very high. And at that resolution, the models can robustly fit data without needing standardized resolutions beforehand. The AI forms an initial guess of the atomic model. But to verify that guess, the suite relies on a neural network called RMS-FNet.
Okay, let's pause on RMS-FNet.
Yeah.
Because if I'm looking at a predictive model, it's essentially handing me a digital coordinate map of where it thinks the atoms are, right?
Correct.
And the cryo-EM is an experimental density map. It's the actual physical evidence.
Right.
I'm just struggling with how a neural network mathematically compares the two without, a human in the loop eyeballing it to say, yeah, that matches.
What's fascinating here is how it achieves this through what the researchers call interactive dual-feature validation.
Dual feature.
Right. The system utilizes a dual-channel input. It takes the AI's predicted protein structure and converts it into a voxelized density map.
A voxelized map. So like a 3D pixel grid.
Exactly. Imagine a three-dimensional grid where each voxel, each 3D pixel, contains a calculated density value based on the AI's predicted atomic coordinates.
Okay, I'm with you.
Then it literally concatenates that predicted 3D grid with the actual experimental cryo-EM density map. It merges them into a single 2-channel tensor.
Oh, I see. So it isn't just holding up two pictures side by side.
Wow, not at all.
It's more like taking a 3D topographic map generated by the AI and like mathematically subtracting the real-world topographic map of the cryo-EM scan from it.
Yes.
And if the AI hallucinates an atom where the experimental data shows empty space, that mathematical subtraction doesn't equal 0.
It instantly flags a deviation. That is the perfect way to visualize it. The reports refer to this as consistency checking.
Consistency checking.
Right. It is constantly petting the mathematical expectation of the predicted model against the structural variance found in the physical cryo-EM map.
Wow.
Yeah, by forcing these two channels to interact bidirectionally, the agent detects structural deviations immediately. It physically grounds the AI's initial guess.
That makes total sense for mapping a structure. But here's my major concern with this approach. A topographic map is static. A crystal structure is static. But in real biology, proteins are thermodynamic ensembles. Like, they are highly dynamic, jiggling machines.
Well, always moving, yeah.
Right. So if the AI is only verifying its prediction against a frozen density map, isn't it just designing a drug for a statue?
That's a huge problem.
Because when that protein actually moves in the human body, that static match is going to fail, right?
You are touching on one of the greatest grand challenges in computational biology right now, the validation of structural flexibility.
Structural flexibility.
Yeah, standard AI structure prediction, the kind we've seen dominate headlines over the last few years, it often ignores protein dynamics entirely.
Really? It just pretends it's frozen.
Basically, yes, it gives you a highly confident, completely frozen conformation. But if a therapeutic ligand is trying to bind to a receptor pocket, that pocket is constantly fluctuating.
Right.
And the brilliant thing about cryo-EM data is that it inherently contains dynamic information.
Wait, how does a frozen scan contain dynamic information?
Because the density map is reconstructed from thousands of individual particles frozen in slightly different conformational states. So it captures the blur, it captures the structural fluctuations.
Oh, wow. So the AI can actually read the fuzziness in the cryo-EM map to understand the thermodynamic movement.
Exactly.
But how does it quantify that? I mean, fuzziness isn't exactly a highly rigorous metric for drug design.
Well, it quantifies it through dynamic indexing. This is the second major function of RMSFNet. It uses the variance in the cryo-EM data to predict the root mean square fluctuation, or RMSF.
Okay, RMSF, what does that actually measure?
Mathematically, RMSF measures exactly how much a specific amino acid residue deviates from its mean position over time.
Basically, how much it jiggles.
Exactly, how much it jiggles. And the precision the suite achieves here is just remarkable. They are hitting correlation coefficients around 0.74 at the voxel level and 0.76 at the residue level.
0.76. So just to contextualize that for anyone listening who works with molecular dynamics,
Yeah.
getting a 0.76 correlation coefficient without having to run massive computationally expensive MD simulations for weeks on end, that is a massive leap.
It's huge.
It's providing a rapid experimental baseline for flexibility almost instantaneously.
It's a total game changer for efficiency. It allows the scientific intelligence suite to instantly recognize which domains of the target protein are rigid and which are highly flexible.
So what does this all mean for the actual drug? Like, it's great that it knows a certain loop on the protein is flexible, but when we move to the drug generation phase, how does knowing the variants change the actual chemical design of the therapeutic?
It fundamentally alters the lead optimization phase through a procedure called Libero.
Libera.
Yeah, it stands for ligand-guided receptor optimization.
Right.
So when the AI is refining how a generated binder fits into a pocket, Libero doesn't just look at the drug.
What else does it look at?
It optimizes the receptor's side chains and the surrounding water molecules specifically within the binding pocket identified by the cryo-EM. Yeah, and because it has that RMSF data, it ensures the newly generated binders are validated against a realistic ensemble of protein states.
So not just a single snapshot.
Exactly. The AI knows the physical constraints of the lock's movement, so it designs a key that works across the entire range of that movement, not just a frozen moment in time.
Okay, so the AI has a perfect dynamic map of the biological lock. But, having the map of a lock doesn't mean you know how to forge the chemical key.
Very true.
I want to shift to the generation side of the equation. Here's where it gets really interesting. When we let generative AI actually draw the molecule, using models like Proteina Complexa mentioned in the reports, how do we stop it from drawing a key made of imaginary metal?
Right.
Generative models are inherently probabilistic, right? They want to find patterns, even if those patterns completely violate biophysics.
Yes, and this is the most critical safeguard in the entire architecture. You simply cannot allow a generative chemistry model to run unconstrained.
It'll just hallucinate.
It will hallucinate constantly. So to prevent the AI from producing hallucinated structures that lack biophysical validity, the suite employs inference time optimization.
Inference time optimization.
Yes, it actively steers the generative process using strict physical energy potentials.
Okay, this is where the translation of physics into code gets fascinating to me. How exactly are they steering it? Are they just like applying a filter at the very end of the generation process?
No, applying a filter at the end is way too late. By then, you've already wasted the compute.
Makes sense.
Instead, they use biophysical reward functions integrated directly into the search algorithms. The AI uses algorithms like beam search or Monte Carlo tree search, MCTS, to explore possible molecular configurations.
Okay.
And as the MCTS explores different chemical branches, it is constantly being fed rewards based on hard physics. For example, it calculates interface hydrogen bond energies.
Oh, so it's doing the physics math on the fly.
Exactly. It also derives physical energy-based metrics from established thermodynamic models like Rosetta.
So the search algorithm isn't just asking, does this chemical structure look like the training data?
Yeah, not at all.
It's being forced to ask, is this specific molecular configuration energetically favorable in the real world?
Precisely. It pushes the model toward configurations that are not just structurally confident, but thermodynamically stable. And that predictive layer, the IsoDDE model we mentioned earlier, it acts as an incredibly strict geometric bouncer.
A geometric bouncer. I love that.
Yeah. It implements rigorous stereochemical filtering. It examines the local bond angles. It looks for deviations from planarity in sp2 carbons. It checks for incorrect stereochemistry in chiral centers.
Wait, let me dive into that bouncer analogy, because the sources highlight a very specific threshold for intramolecular clashes.
Oh, the clash threshold, yeah.
Yeah, if the AI proposes a molecule where two non-bonded atoms are too close to each other, the suite calculates the sum of their van der Waals radii. And if they approach closer than that sum, minus a 1.5 angstrom threshold, the design is automatically marked as a violation and trashed. It literally checks if the atoms are trying to occupy the same physical space.
It does. It enforces the Pauli exclusion principle in real time. If the model hallucinates a clash, the pathway is terminated. Bouncer says no.
But I'm looking at this from a computational perspective, and I see a massive potential bottleneck.
What's that?
Well, generative AI builds things step by step, right? Often starting with a noisy, low-resolution approximation of a molecule and refining it.
True.
It's like trying to judge a cake by tasting raw flour. If you apply a strict Rosetta energy score or a van der Waals clash check to a half-finished, noisy intermediate state, it's going to fail the physics test instantly.
Every single time.
The intermediate states of drug generation are a thermodynamic nightmare. So how does the system not just delete every single attempt before it has a chance to form into a stable molecule?
You've identified the exact reason why early generative models really struggled to produce viable compounds.
They were just deleting everything.
Pretty much. If you score noisy intermediate states, your reward functions will penalize and discard perfectly good chemical pathways simply because they aren't finished yet.
Right.
This scientific intelligence suite solves that bottleneck by performing stochastic rollouts.
Stochastic rollouts. Walk me through how that bypasses the noise problem.
Rather than scoring the intermediate state directly, the suite takes that candidate state and simulates it forward. It rolls it out into a fully denoised, clean structure.
Oh, wow.
Yeah, it essentially fast-forwards the generation process to see what the final stable molecule would look like if it continued down this current path. Only then does it apply the biophysical reward functions and the Rosetta metrics.
Ah, that is incredibly clever. It's evaluating the potential of the pathway, not the messy reality of the intermediate step.
Exactly.
It allows the AI the mathematical freedom to traverse noisy chemical space, knowing that the final evaluation will only be conducted on a biophysically realistic sequence.
It is a massive computational optimization. It ensures the AI is guided by the true physical endpoint, avoiding the trap of local minima caused by temporary generative noise.
Okay, so this strict physics-based architecture, the RMSSnet, the biophysical reward functions, the stochastic rollouts, it all sounds incredibly robust when we are dealing with well-characterized biology.
Absolutely.
If we have high-resolution cryo-EM maps and tons of historical data, the system works beautifully. But if you're a researcher listening to this, you know that the most pressing challenges in drug discovery happen on the frontier.
The unknown.
Right. What happens when the system is hit with a novel pathogen? a target where traditional homologous data is scarce, or we're in completely uncharted chemical territory.
Yeah.
How does the AI operate when its training data basically runs out?
This raises an important question, and it's the ultimate test of scientific intelligence versus just standard machine learning.
Okay.
A standard model encounters out-of-distribution data and fails. It just outputs garbage. But this suite is designed to adapt to the unknown through a mechanism called protein test time training, or protein PTT.
Test time training, meaning it is actively updating its own parameters while it is performing the inference.
It is. When the suite is assigned a completely novel target protein, say, a newly sequenced viral receptor with no known evolutionary cousins in the database.
Which happens all the time.
Right. It performs self-supervised customization of its language models on the fly. It analyzes the specific target sequence and actively works to minimize the model's perplexity.
Perplexity being the AI's internal metric for uncertainty or confusion.
Yes. By actively minimizing its perplexity on that novel sequence before it even begins the prediction phase, protein TTT generates highly accurate representations for both structure and function.
That's amazing.
The benchmarking in the reports shows that protein TT successfully improved structure predictions for 19% of viral targets, where traditional homologous data simply didn't exist.
19%.
Yeah. It recalibrated its understanding of the underlying physics just by studying the sequence itself.
So it realizes it doesn't understand the target. It stops, teaches itself the underlying patterns of that specific sequence, and then proceeds.
Exactly.
Okay, that handles the biological target side. Does it employ a similar strategy when exploring completely novel chemical spaces for the drug itself?
It does, but through a different mechanism called ChemScreener, which is an active learning workflow used during lead optimization.
Okay, ChemScreener.
Yeah, when the AI is navigating vast, unmapped chemical spaces where its predictive confidence drops, ChemScreener utilizes an ensemble uncertainty strategy.
Let's unpack the ensemble uncertainty strategy. That implies it's running multiple predictive models simultaneously, right?
It runs an ensemble of models, yes, and it looks for where those models violently disagree.
Oh, interesting.
Yeah, if the models all predict the same outcome, the AI knows that chemical space is well understood. But if the ensemble produces wildly different predictions for a specific chemical region, the system flags that area as novel chemistry. It explicitly identifies its own blind spots.
And what does it do with those blind spots? I mean, it can't just simulate its way out if it has no baseline physics to draw from, right?
Exactly. It prioritizes them for experimental validation in the physical world.
Wait, really?
Yes. It takes those low-confidence, high-variance chemical structures and sends them to automated, self-driving laboratories to be physically synthesized and tested.
That is wild.
By purposefully exploring the areas where it is most ignorant, it maximizes the information gained from each physical experiment. The empirical data is then fed directly back into the AI to resolve the uncertainty.
Wow.
And this active learning loop skyrocketed their hit rates from a baseline of 0.49% to an average of 5.91%.
Okay, if you were an investor or lab director listening to this, a jump from 0.5% to nearly 6% might sound like small numbers, but
In drug discovery.
exactly, in the context of drug discovery, that is a monumental leap in efficiency. That is the difference between synthesizing 10,000 useless compounds over 5 years and finding a highly viable drug candidate in a matter of months.
It turns R&D from a massive dragnet operation into a highly targeted laser strike.
And it's entirely due to the closed-loop feedback between the digital models and physical reality. The AI isn't just a software program generating files in a vacuum. It interacts with the physical world, learns from the empirical thermodynamics of the molecules it designed, and instantly refines its biophysical understanding.
It's a continuous cycle of learning.
So, bringing this all back to you, the listener, why should you care about the minutiae of RMSFnet, or stochastic rollouts, or voxelized density map concatenation?
Because it's life or death.
It really is, because the gap between a promising AI prediction on a computer screen and a physical pill that actually cures a disease in your body relies entirely on whether that algorithm respects the laws of physics. Generative AI is easy. Anyone can prompt a model to draw a molecule. But accurate, biophysically grounded AI is incredibly hard. By using cryo-EM to anchor itself to experimental variants and filtering out physical hallucinations with strict geometric bouncers and utilizing active learning loops to teach itself when it hits the unknown.
It's changing everything.
Yeah, this architecture is quite literally rewriting the timeline for human therapeutics. We are looking at a future where responding to a novel biological threat is measured in days and weeks, not decades.
And, looking at the trajectory of this technology leaves us with a rather profound horizon to consider.
Yeah?
We have spent this entire discussion exploring how these AI agents are strictly constrained by the physical laws of natural biology, how they are forced to perfectly map the dynamic fluctuations and thermodynamic realities of natural proteins just to design drugs that fit them.
Right, that's the whole safeguard.
But if these systems now possess the atom-by-atom understanding of biophysics required to map and manipulate natural life so flawlessly, what happens when they flip the script?
What do you mean?
What happens when these autonomous agents are tasked not with curing natural biology, but with designing entirely synthetic biological machines? Proteins, enzymes, and cellular mechanisms that wiggle, function, and operate in physical ways that evolution never even thought of.
Wow, that is a staggering thought. Moving from reading the biological blueprint to writing entirely new laws of cellular machinery.
Exactly.
It changes the definition of what life can be. Well, thank you so much for joining us on this deep dive today. Stay insanely curious. Keep questioning the models around you. And remember, just because the algorithm designed the blueprint doesn't mean you shouldn't check the physics. We'll catch you next time.